All right. Like I said, I don't know how long this is going to last. So take notes today. Questions on homework? 41. 41? On what page was that? Because didn't I give 2 assignments? The first one? Was it the one where you were trying to find the inverse?
Yeah.
It was the cube root?
Yeah.
Okay. So you're given f of x equals cube root of x minus 2, that one?
Yeah.
Right? Okay, so you're asked to find the inverse. So the first step for finding the inverse is to replace f of x with y. The next step is to replace or swap your variables. Right? And then now solve for y. So to get y by itself, we actually have to get rid of that cube root. So we cube both sides of the equation. That means I will take x on the left side, I will cube it. I will take the cube root of y minus 2, and I will cube it. So cube both sides. When I cube a cube root, they go away. And so you're left with just x cubed minus, or equals y minus 2. And now you almost have y by itself. You just add 2 to both sides. And you're there. That make sense? And then replace your y with f inverse, and you're done. So the fourth step, f inverse x is x cubed plus 2. That's it. Okay. Any others on homework?
73?
Same page?
Yes.
Okay, so that'll be almost the opposite of what we just did. It's x minus 1 cubed over 8. 73. So I replace my f of x with y. I now swap the variables. And then try and get y by itself, right?
Yeah.
So I have a fraction here. I'm going to clear the fraction by multiplying 8 on both sides. When I multiply 8 over here, I get 8x. When I multiply 8 over here, it cancels out. So I get the y minus 1 cubed. And now I need to get rid of that cube because I have the y is trapped inside this parentheses. So I need to get the cube out of there, so I cube root both sides. So I will do cube root. And when you do cube root, do you have to do plus or minus? No. Cube root. And when I do the cube root of something cubed, it goes away. So on the left, I still have cube root of 8x. On the right, y minus 1. And now I just add 1 to both sides. Okay? So cube root, 8x, and then just be careful, this plus 1 is out here by itself. You don't do plus 1 underneath the root. Plus 1's over here. And then replace y with f inverse, and that should work.
In the answer, it says 2 to the cube root x plus 1.
You need it broken down more, is that fine?
2 to the what?
It was,
There's a 2 in front of it.
Oh, I know it. Okay, yes. They did what's the cube root of 8. So, all right, this would be fine on the test, what I just boxed there. What they did is they said, okay, you have cube root of 8x. Property of root says that you can break this into 2 roots separately because there's multiplication here. And the cube root of 8 is the number that you would multiply times itself 3 times to get 8, which is 2. So this right here is a 2, and then cube root of x. Is that what they have?
Yes.
and then the +1.
What was there, 3 and then 2 and then 3x? That's fine.
That should be what they have. Any others? Okay.
Oh, good.
Well, while you're looking there, today is the last day to drop a class for summer, right? Did I mention that last class?
Yeah.
Today is the last day you can drop a class. So what I did is I went online, I updated, make sure all your grades were up to date. I did that earlier today, so you might want to just double check. What I've done is you're going to have 3 exams here. We'll say E1, Exam 1, Exam 2, Exam 3, and then you have a final, right? This is 20% of your grade, 20% of your grade, 20% of your grade, and then 25% of your grade. And then the remaining 15% is homework / quizzes. So I haven't really done a homework check. I've given you a few quizzes. We've taken this, right? We've already done that. We still have the other 2 exams. So here's what I'm going to do. I'm going to, if you go online and look at your grades now, you'll see all of this stuff here. And under homework and quizzes, you're going to see homework, I think 1, homework 2, homework 3, homework 4, and then quiz 1, quiz 2, or something like that. So what I'd like for you to do is I'd like for you in the over the weekend, next week, start to gather together your homework, right? I've asked you to do your homework, keep it in one place. And next Thursday, we're supposed to, is when I plan to have our next test. Okay, next Thursday. On the day of the test, what I want you to do is come in with your homework and have it in some format that you can give it to me, and I'll look at it during the test. So if it's mixed in with your notes, because I know some people put it in their notes, that's okay, as long as I can tell where it is. And what I'm going to do is I'm going to give you, on Thursday, I will give you 3 homework grades based on what you turn in to me. So it just needs to be like, you've made an honest effort at the homework. I can tell you did it, right? That's all I'm looking for. And then the last homework grade will be the information we cover after that test, okay? All right? You don't have to have every single problem done. If you're missing, 1 homework set, that's okay. I just want to see that you've been doing homework throughout the semester and give you credit for that, right? We clear? All right. The goal of this is not for you to go, like you've done no homework all semester, and now this weekend you're going to go try and do all your homework. I mean, you could do that, but that's not the point. The point is you should have been doing it to begin with. All right. Questions? You may want to know, like, where do I stand in the class? What do I need in order to pass the class? If you are concerned at all about your grade, I'm going to take the last maybe 10, 15 minutes of class. I'll stop class a little early. I'll give people the opportunity to come and sit down with me, and we'll just look at what you need, where you stand exactly in the class. All right? Yes?
Are there 2 quizzes?
I believe so. I believe so. And I've graded everything, and I have it all that I can hand back to you. And I'll do that when we take our break. Pass everything back. Okay. Well, let's pick up where we left off. Was there another question, or?
No, I just number 61 on 432 as we see Thursday. A good way to do that. What is the easiest way to do that?
Okay, 1/5 x equals 125. That one? Well, there's different ways that you can approach this. This is where we're trying to solve for x, right? And what we had done before is we tried to get both of the numbers here to be like the same base, but it's difficult to see how 125 might be somehow connected to 1/5, right? So let me show you way you could do this. Tell me if you agree with this or not. Is that the same thing? Yes? Taking 5, raising it to the -1 is the same as 1/5. And then on the right-hand side, 125 is 5 to what power? Third power, 5 times 5 times 5. So, do we have the same base now? Yes. Okay, what is this going to be here? Something to a power to a power. What do I do to these powers? Multiply. So that's really 5 to the -x, isn't it? Must equal the other side 5 to the 3. And now this must equal this, right? Since they have the exact same base. So -x must equal 3. And if I multiply both sides by -1 or divide by -1, I get x is -3, right? Make sense? You do it a different way?
Yeah, but I didn't get the same answer.
So it's a little tricky here, this part right here. Same map. Is there another way to do it? Let's see. What if I had done this instead? What if I left the left side alone and I realized that the right side is 5 to the 3rd, right? Can you rewrite 5 with the 1/5? So can you, would this be the same thing? What's 1/5 to the -1? It's 5, right? You flip the fraction over, but then that's all being what? See, it looks a little weird here. Cubed. You'll see that this right here is 5. 5 cubed is 125. And now, what do I do to these powers? Multiply them. So the left side is 1/5 to the x. The right side is 1/5 to what power? You said you multiplied those, right? -3. And now this has to match this, right? So x has to be -3. You get the same answer. Either way would have worked. I can't really think of another way that that would have worked, though. But after today, we'll have a way of doing this without having to do it by hand. We can use our calculator, which I hope you brought, because it's going to be a quiz grade today. Remember, I even brought one. Okay, we'll see. All right, we need to continue on. We finished up 4.2, right? And we're going to get into 4.3. Which is titled Logarithms. And I'm just going to say log functions. When I say log functions, I mean logarithmic functions. Functions that involve logarithms. Logarithms always present an issue for students. In the entire history I've been teaching, students have trouble with logarithms because it's something new for a lot of students, and so the notation of it is confusing. So let me try and do my best to make it as simple as possible for you. Let's start with something like this. Does everybody agree that 4 squared is equal to 16? Yes? We will call this right here exponential or exponent form. Now the reason we're going to call it exponent form is because you see an exponent here, don't you? See the exponent is 2? We have something being raised to a power, the 2 is the exponent. We have another way that we can write this, all right? But let's talk about what this is saying. This is saying 4 to the second power is 16, right? 4 to the second power is 16. The other form, which I will call log form, is written this way. Right, so the left side here is what's called exponent form. This is an equation, right? We all agree this is a true equation? This is exponent form. This is another equation. It's called log form, and this equation is also true. Now, what is this equation saying? To get you to see how this equation works, let me go back to this. If I cover up to 16, if you say 4 squared, everyone here can just tell me what it is, right? 4 squared means 4 times 4, which is 16. But if I come over here and I say log of 16 base 4, and I'll write this down how you would say that. But log 16 base 4. We know the answer is supposed to be what? 2. But then what is this really saying to you? How do I get 2 from just those two numbers? Am I saying 4 times what gives me 16? No, right? 4, because 4 times 4 is 16, right? I'm saying 4 to what power gives me 16, right? And the answer is 2. Here I'm saying it's obvious. 4 squared, 4 times 4 gives you 16. Here you're saying 4 to what power, question mark, gives you 16, answers 2. You see the difference? Let's try another one. How about if I write 3 to the third equals 27? That's exponent form, right? We all agree with that statement? In log form, it would look like this. Log, what would this little subscript number down here be? 3, and then what number would go here? 27. So what we're saying to ourselves, and I'm going to try and get an answer here, is we're saying to ourselves, 3 to what power gives us 27? 3, right? So anytime we have something in exponential form or exponent form, we can convert it to log form. Try something a little more interesting. How about this? 4 to the x equals 64. Now that's an equation, right? That's an equation, but it has a variable. This would have been something like you would have had on your homework, right? This is an exponent form because we have an exponent, don't we? But I'd like for you to write it in log form instead. Aren't we saying to ourselves to answer this question, 4 to what power gives us 64? But in log form it would be what? Log, the little subscript here would be 4, right? 64 here, and this side should be x, whatever x is, right? That's what we're trying to find. So again, cover up the x, we're saying 4 to what power is 64? That's the same as this equation, isn't it? It's saying 4 to what power is 64, but written in a different form, it looks like this. So all a logarithm is at this point for you is another way of writing an exponent, right? It's just a different notation. All right? Let's try and write something else down. How about 4 to the 3 halves equals 8. Write that in a log form. That's an exponent form, right? Write it in log form. So I'll just do an arrow. Log, what's the little subscript here? 4, what goes here? 8 equals 3 over 2. Understand it's just another way of writing something? That's all it is? Okay. Let's get some wording down. If you write log with a little subscript like this, then what that is, it's a logarithm of base A. Okay, it's logarithm base A. So this A down here, we call the base of the logarithm. What was the base of an exponential function? Remember when we were talking about exponential functions last class? If I had 2 to the x, that was an exponential function. The base here would be what? 2, right? But with logs, whatever number's down there is the base of the log, all right? We have some restrictions on this. The A down here has to be bigger than 1, or sorry, bigger than 0. And the base down there cannot be 1. Does that look familiar? Remember with exponential functions, we had the same condition, right? The base had to be bigger than 0 and couldn't be 1. Same goes for logarithms. That's what we call it. That's a log base A. Let's see if I give you a log, if you can take it to exponential form instead. So if I write log base 10 100, convert that to exponential form. I'm going to put exp here. Convert that to exponential. Well, you know what? I forgot to put the answer. Equals, what is that equal to? 2. Why? Because 10 to what power is 100? 2, right? So that's 2. Convert that to exponential form. It's what? 10 squared is 100, right? Now we have to be very comfortable converting back and forth from exponential to log and vice versa. So I have a way that I like to show my students, a way to remember how to convert logs to exponentials. If you're given a log, here this would be log base what? Base A. If you're given this equation, to convert it over to exponential, I will use what I like to call the loop. Okay? The loop. It's a loop. Okay? Here's the loop. You take the base, you loop it around to the y, loop that back into the x. So what we're saying is to convert this to exponential, we will take A, we will raise it to the y, right? And that will then need to be equal to whatever was here. Do y'all agree with that little loop thing? You'll see it? Like back here at this, if I want to convert that to exponential, I take the 10, I raise it to the 2, and set that equal to whatever was in here, 100. See it? That'll become very useful later on. Okay. Let's talk about a few properties of logs. Okay, some of the properties of logs, and there's a lot of properties for logs. Let's see if you understand this or not. Let's see, our first property. What is log base A of 1? So what's the question you're asking yourself? A, right, raised to what power gives you 1? 0, right? Anytime you take a number raised to the 0, you get 1. So the answer here is 0, right? Does it matter what A was? That could have been a 4, it could have been a 10, it could have been a 9, right? No matter what the base is, if I take it and I write log base A and I put a 1 here, no matter what, I get 0. With me? Regardless of A. So that's a property of a log, because that means for every log, if I try and take log and plug 1 into it, I get 0. How about this? Log base A of A. So you're saying A to what power gives me A? First power, right? A to the first power. So if the base matches what's in here, your answer is always 1. Does it make sense? Next to this, what I'll do just to convince you more is I'll just draw the loop real quick. This says this to that is this, right? That's saying A to the 0 is 1. We agree with that? How about this one? This is saying A to the 1 is A. A to the 1 is A. Is that true? Yes. What about this? What is that?
X.
X? Because we're saying A to what power is A to the X power. That means that it would have to be X, right? So that if you do the loop, A to the X, does that equal that? Does A to the X equal A to the X? Yes. Do you follow this or not? Okay. So those are some of the properties of logs. We'll get back to those. We'll be using those. So let's talk a little bit about logs as functions. So if I define a function to be log base A of x, then what's the thing I'm plugging into this function? Plugging in values of x, right? In here. And it's spitting out a number. This is called the log base A function. So let me give you a specific example of a log function. And I'll use the function, the log function is very similar to what we started with exponential functions. Log base 2 of x. I would like to create a t-table quickly to try and figure out what happens if I plug in x. What does this function spit out? So somebody give me a value of x to plug in. 3? Okay, if I plug 3 in here, are you going to be able to tell me what the answer is? So I'll put it over here on the side so we can think about what's happening. All right, log base 2, 3. That means 2 to what power is 3, right? Does anybody know what power you raise 2 to get 3? Not offhand, right? So 3 probably won't be a good number to try here. Remember with exponential functions, it didn't matter what we tried, right? They all worked out pretty good. With logs, you have to be careful what you plug in here. What do I know? I need to know powers of 2, don't I? So what would be some good numbers to use here? 4 would be good. 8, 16, right? I could try those. How about, could I put a 1 in there? Didn't we say if you put a 1 in any log, it always spits out what? 0, right? So I could do that. We said 2. How about 2? We didn't say 2, but 2 would work, right? We plug 2 in here. Don't we have that property we just looked at? So if you have 2 here, it's like A and A. That spits out 1, doesn't it? What if I plug in 4? Okay, 2 to what power would give you 4? 2. What was the next one you said would work? 8. 2 to what power would give you 8? 3. With me? And we can keep going. The next one we probably use would be like 16 and then like 32, right? Okay. Can we plug 0 in? Can you plug 0 into a log? Let's try it. I'm gonna try and plug 0 into this. What's log base 2 of 0? 2 raised to what power gives you 0? 2 to the 0 gave us 1, remember? Right? When we plugged in 1 in there, right? 2 to the what gives you 0? It's not possible, okay? It's not possible to raise 2 to a power and get 0. This cannot happen, right? So this cannot be computed. In fact, not only does 0 not work, but if you try any negative number, 0 doesn't work, and if you try a negative number, it will not work. Because 2 raised to any power can never be negative. Why is this true? I'm trying to make a connection to last class. This base is positive, right? It might be a little bit of a stretch. Will you just take it on faith for right now, and then I think I can bring it to light once I show you a pattern that's happening here. All right, just trust that this won't happen. This can't happen. All right? Here's a tricky one. Can I plug in 1/2?
Yes.
Yes? Why? Because 2 to what power is 1/2? -1. Do you agree with that? 2 to the -1 is actually 1/2, isn't it? That's what that is. So 2 to the -1 is that. So that's true. So I can put a 1/2 in here and it's fine. I can't put 0, I can't put negative numbers, but I can put fractions in. Now I want you to think back to last class. Do these points look familiar to you? One 0 2 1 4 2 8 3 from last class. That's right. Aren't those the same points that we got when we were trying to graph? I asked us to graph the first exponential function we ever graphed last class was this one, right? And when we made a t-table, we plugged in 0, we got 1. We plugged in 1, we got 2. We plugged in 2, we got, what do we get? 4. When we plugged in 3, we got 8, right? Aren't those points flipped over? In fact, if I were to do it this way, what did we plug in here? We plugged in 1/2, right? Here, and it spit out -1. What happens if we did it the other way here? -1 into the exponential, didn't it give us 1/2? What does this mean? Drum roll. 5 points, next test. Who's got it? You got your hand up. That's right. Because I said last class, the property of the inverse is that it was every point flipped, wasn't it? Like if we were trying to graph an inverse, we just take the x's and y's and switch them. Can you see that this log base 2 function, I erased it, that if I say f of x is log base 2 of x like that the ordered pairs for that function are exactly the ordered pairs for this function flipped over, which means that these are inverses, which means this function is the inverse of this. This one undoes that one. You with me? So that means if I were wanting to graph that, right? If I were wanting to graph that, what I could do, because this was kind of hard, right, to pick those points. We had to think about it a little bit. Okay, I could plug in 1, plug in 2, I can plug in 4, I couldn't plug in 5, right? It was kind of hard to think through these numbers. If you were to really try and be clever, couldn't you say, hey, look, I'm trying to graph log base 2. I know that it's the inverse of this one. So why not just make a t-table on that and then do what? Flip them. That's exactly the way we're going to do it. All right? So I'm going to start with a brand new example. I want us right now to sketch the function f of x equals log base 4 of x. So the approach here requires that we understand that the inverse of that function is what? What's the inverse of that? F inverse of this function is what? 4 to the x, right? That's what the inverse is? And can I make a t-table for that function? Can you make a t-table for that? What were the numbers that I said you should plug in when graphing exponential functions? I said we'd always use the same ones. 0, 1, 2, 3, negative 1, negative 2, negative 3. So that's what I'm going to do here. 0, 1, 2, 3, negative 1, negative 2, negative 3. If I plug in 0, what do I get? What always happened? You get 4 to 0 is going to be 1. If I plug in 1, what do I get? 2, 16, 3, 64. Plug in negative 1. 1/4, negative 2, 1/16, and then finally 1/64. Understand? Now I'm ready to graph this. So let me come back to f. I know something about its inverse, right? All I need to do now is take all these points and swap them, right? Swap these. So to graph the points on that, I'm going to take, let's see, 0, 1 becomes what? 1, 0. 1, 4 becomes 4, 1. 2, 16 becomes 16, 2. You see how this works? And then the last one. So logarithm is another way of writing an exponential, right? In fact, a logarithm is exactly the inverse of an exponential. So let's try and draw this graph. And before I draw it, let's talk a little bit about what my graph's going to look like. Like, you know, am I going to be over here? Or remember what exponentials look like? Right? Exponentials look like this or like this, right? Remind me to give you the 5 points, because I'll forget. Okay. Right? Remember this was what exponentials look like? We called this one what? Exponential growth. This one was decay, right? That's what exponential looks like. So with exponentials, you really didn't need all this down here, right?
No.
So for logs, what is it that we need? Well, let's look at our x values. What do you notice about all these x values? They're all positive, right? Now your y values are what? Both positive and negative. So it looks like my x values are positive, and then my y's are both. Here with exponential, what was positive? My y's were positive, and my x were both?
Yeah.
The inverse is actually opposite of that. My x's are positive, and my y's are both. So let's draw it. See what it looks like. I'm going to draw it like this. I'm going to raise that up because I'm going to go off camera. All right, let's start with the first point. 1, 0 is here, right? Next one is 4, 1. Out 4, up 1, here. Next one, 16, 2. That's way out there. (16:2). Somewhere around there, right? Where's the next one? 64:3. I'm not going to draw that one. Do we realize it's way out there and it's just up a little bit? right? Okay, so I'll scrap that one. It's not going to fit on my graph. All right, what about this next one? 1/4 -1. That means I move to the, starting at the origin, I move to the right 1/4, right? Just barely, and then come down 1. Does that look about right to you?
Yes.
Then the next one, look at that. I move to the right how much? 1/16, just barely, right? And come down 2. What about the next one? Move to the right, what? 1/64, and then come down 3. What's happening here? We have an asymptote. It's getting closer and closer, right? But it keeps going down. And remember we said we couldn't be 0? I said that a little while ago, and I said that you couldn't plug negatives into a log. So this goes down like this. And it goes up like that. Now it keeps going up. It's just going up slowly, isn't it? That is the graph of the logarithm. Now, if I were to draw a diagonal in here and reflect it over, what would it be? Exponential. It would be the 2 to the x, wouldn't it? And if I were to graph 2 to the x up here, and you don't need to here, but if you were, it would look like this. Remember exponential did this, and then it took off like that? Can you kind of see that they're like mirror images? Okay? So now let me get back to something that I kind of waved my hands at. This was 2 to the x. We made a t-table. It was 0 gave us 1, 1 gave us 2, 2 gave us 4, 3 gave us 8, -1 gave us 1/2, -2 gave us 1/4, -3 gave us 1/64, right? That's what we had done? I had told you that when you have log base 2 of x, that you cannot plug 0 in here, right? I also said you can't plug a negative number in here. Do you see why from this table? Remember, this right here, if we flip them, right? We flip them, we get the table here. These are the things we plug in. What is about these? They will never be what? They'll never be negative, and they'll never be what? 0, right? So what's coming out of the exponential function is actually what becomes what goes into the log. So if what comes out of an exponential can never be 0, can never be negative, then that means that what goes in a log can never be 0, can never be negative. So maybe you made that connection, maybe not, but that's the reason why. Okay, so do you think if I gave you a log function with a different base, right? If I gave you like log base 3, you think you could graph it? How would you go about that? How would you graph that? Not asking you to do it, but how would you do it? What would you start with? The inverse, right? 3 raised to the x. You'd make a table off of that. Take that table, then do what? Flip the points, plot those points, you're done. Right? Okay. So how about this? What if I were to give you a problem like this? Sketch f of x equals log base 4 x minus 3 plus 1. What have I done? What have I done here? What is that minus 3 inside there going to do? It's going to shift it, right? What does the plus 1 do? It's going to shift it. But what's it going to shift?
Right 3.
Okay, right 3, not 1. But what is it that it's shifting? That log, right? The log base 4. We almost want to look at, like, our toolbox function here would be the log base 4 function, right? That's the one that we would draw, and then we would move it. Understand? So to do this problem, the first thing I would do is I would say, I'm interested in this, right? What does that look like? How do I graph that? I draw its inverse first, right? And then I get my t-table from that, and then I flip the numbers, right? Which is what we just did. That's the exact same problem of what we just did. And we drew it, didn't we? So what I would do now to draw this, I would have to go through all the work I just did a second ago. I would take that graph that I drew, which looked like this, right? And I would need to move it. I would need to move it what? Right 3, up 1. So let's grab this point right here. I'd move it to the right 3, and up 1 would put it here, right? And now it's going to go down, and it's going to come this way. Now, what happens to that vertical asymptote? It goes how far? Right 3, doesn't it? It comes, since the whole graph shifted, the asymptote's going to come also. So if I go to the right 3, 1, 2, 3, come down, draw my vertical, then I can see that this point was going to dive down like that, and it's going to come up like this. Does that kind of make sense? This right here is a good example of an exam problem. Because in that one problem, you have to first identify what the base function is, then graph that, which requires you to look at its inverse, make a t-table, then switch the ordered pairs, graph it, and then move it. You all right? Got to wake up or leave, one or the other. Okay. Questions? You have some homework problems like this that I'm not having given you your homework yet, but you're going to have 3 homework problems that are going to be to draw these. Okay, well, that's as far as we're going to go with graphing logs, right? That's pretty much it. We're going to investigate logs a little deeper now. Do you recall from last class the 2 special exponential functions? Remember what they were? What were the 2 special ones?
Base 10
Base 10, so it was 10 to the x, right?
and base E.
And base e. And I asked you to make sure that you knew on your calculator how to do e to different powers, and it was part of your homework assignment, right? So if there are 2 special exponential functions with those 2 bases, 10 and e, then wouldn't it make sense that there are 2 special log functions also with those 2 bases? And that's exactly what we have. There are 2 special log functions. They are f of x equals log base 10x, and the other one, here I'll split these up. The other one was f of x equals log base what? E of x. Now, for those of you who, well, who doesn't have their calculator? Let's do it that way. Who does not? What? Okay, so everybody else, look on your calculator. You should see somewhere in your calculator, hopefully you'll see like a 10 to the x somewhere. Do you see a 10 to the x somewhere? Do you see an e to the x somewhere in your calculator? Yes, 10 to the x. Do you see a log base 10x or a log base ex on your calculator? No? Nobody has a log base ex or a log base 10x on there? Just a button that says log?
Yeah.
Next to the button that says log, do you have one that has an L and an N? An LN?
Yeah.
So some of you have a log, and it's okay. So that's what the hell's going on here. A lot of these calculators have an LOG button, right? And then you have maybe somewhere a different button, or maybe sometimes it's up here instead, or maybe it's attached to this button, like as a shift option or something, right? So show of hands, how many of you have logs sitting right there? Okay, how many of you have this one? Okay, all right. So where the hell are these two special ones? Well, here's the deal. This right here, log base 10, is that one. Okay? When you see log on your calculator, it's implied that it's log base 10. That's what it means. All right? When you see ln over here, it's referring to this log. Now, if you go back in your notes, I believe I called this the natural exponential function. This is called the natural log function, or the natural log. And that's where this comes from. ln is, I believe, like log natural, like French. You know how the French, they kind of do it backwards, right? It's like logarithm natural, or something like that. So it's L, then N. I've had students that think that that's an I, because on calculators sometimes it's just written like this. They think it's IN. It's not IN, it's LN. It's a capital. Oh, I don't know. Okay, so this, the notation we use for this is log x, and the notation we use for this is ln and x. Please understand, this means this. This means this. It's kind of like the square root of x. What's the number sitting out here? If there's not a number out here, what's the number? 2, right? Like if I write this, cube root of x, everyone understands I mean the cube root. But if I don't write any number there, everyone understands it's square. So it's a 2. Well, if you write log without a base written, it's understood to be 10. If you write ln, it's understood to be a log with base e. I think that's one of the most confusing things, because why not just leave it like this? Why have a special notation for it, right? I'm going to explain why. Because I always wanted to know when I was a student, like, well, not when I was later on in my math life. I was like, well, why the hell did we switch over and confuse students by making that one? Then they forget that this is where it came from and everything. So here's why. Anybody here ever used a typewriter? Okay, if you've ever used a typewriter, okay, have you ever tried to subscript on a typewriter? Okay, so you're typing these physical keys. There's a little mechanical thing going, hitting the paper, right? And then you have to actually, to subscript, you actually have to stop. You have to turn like a half rotation on the drum and then type, 10. And then rotate it back and then type X and then continue. Well, these two functions, the log base 10 and the log base E, appear so many times in physics, chemistry, biology, all these different science fields, that when these people were doing research and they were studying things and they were writing these huge papers in journals back in the typewriter days, right? Then what happened was, I mean, imagine if you had to write, if you were a physicist writing a paper, typing it, and you had to put log base E into that paper 400 times. It would just slow you down, right? And think about it. Anybody here ever use Word?
Yeah.
How do you subscript in Word? Is there a keystroke for it? A shortcut keystroke? Maybe. There might be, right? But most people to subscript would have to go up to like an option or something, and it's not a smooth process, is it? So what they decided was, look, if you want to say log base 10, don't even worry about putting the 10. Just write log x. You can type that and never stop, right? I don't have to stop. Just logx, just keep going. Same thing with this one. No subscript required, but I need to be able to distinguish it from this one, right? So we use ln instead of log. Understand? So it was just because it was easier to write things down that way. So every other log out there has to have the base written except these two. Yes?
So if you do put the base, it substitutes that.
That's right. If this base, yes. So if the base is not there, it's 10. If the base is there, then it's whatever that base is. But see, the other bases aren't used very often. All right. So if I were to give you a problem like this, sketch f of x equals this, how would you do that? No calculator. I mean, you'll be able to use your calculator in a minute, but go through the process of, like in the last problem, I asked you to sketch, this is a log function, isn't it? How do we sketch log functions? First thing we did was identified what its inverse was, right? What's the inverse of the natural log? Well, what log is this? See, I think you're already lost. What is, when you see natural log, it really means what? Log base what? E of x, right? That's what that really means? So what's the inverse then of the natural log of x? E to the x, right? E to the x is its inverse. So what I'm going to do is I'm going to look at its inverse, e to the x, and I'm going to make a table based off of e to the x. And we plug in the common numbers that we do for every exponential function. And now you need your calculator, right? Except for the first one. What's e to the 0? 1. What's e to the first power? Approximately 2.718. What's e squared? $7.38. Finally, what's e cubed? 20.08? Okay. Now the true test. What's e to the negative 1? So do you know how to type that in correctly? Yes? What did you get? 0.36? Okay, how about e to the negative 2? 0.13? And finally, 0.04? Now, if you're sitting there just writing this down, that's fine, but you need to make sure you can get these numbers on your calculator. And if you can't, you need to ask for help. Okay, so I looked at the log function. I identified its inverse, which is e to the x. I got a table for it. And now what do I do with that table? Flip it, right? So the points that I'm going to have here are actually 1, 0, 2.718, 1, 7.38, 2. Let's just do those two, because I think the next one, do you agree that's going to make my graph too big? Like it's going to go way off, and I don't really care about that. And then I'll get the others. 0.36, negative 1, 0.13, negative 2, and that should be good enough. I don't need that last one. All right. I'm almost ready for the graph. Now it's going to look something like this. Let's plot these points, but let's plot them very lightly, okay? Why am I going to plot this very lightly? This isn't my final picture, right? What am I going to need to do with my final picture? Move it down 2, right? Don't forget that we had -2 here. So I will take 1, 0, which is here. I will take, what, 2.718. So here's 2, here's 3, 2.7, about here, up 1. See, we're kind of eyeballing this. And then 4, 5, 6, 7, here's 8, so I don't know, somewhere around here up 2. And we already know it's going to do what? It's going to dive down like this. I shouldn't be drawing that solid. I should probably be coming in here and making this like dashed, so you know that's not my final picture. I take that whole thing and do what with it? Bring the whole thing down too. Now, does that do anything to my vertical asymptote? No, because moving it down keeps it still in the same place. It's the left or right that would move the vertical asymptote over. So that's just going to go down. So I'm just going to take every point that I have, right? Move it down to 1, 2. This one's here. This one, 1, 2. That puts it here. This one, 1, 2. That puts it here. And then I draw it again. Still diving down towards the y-axis like that. That's what we would want for that picture. I would. You just subtract 2 from each one?
Yeah.
You could do that. The only thing that would be tricky is if the shift also included a left and right shift. Because if you do that, then you have to also account for that here.
Yeah.
So that as long as you do that, that's okay. I don't have to have both pictures. All right, you think you can handle that? Yay? Nay? All right. Let's talk about the next section. My battery's somewhat holding up. The next section, 4.4. Properties of logs. Log equations, etc. That's not really the name of it. I'm kind of making up my own name for the section. But it's 4.4. We're going to talk about more properties of logs. We're going to talk about how we solve log equations, and then some other stuff that we're going to do. All right. We've already established 3 properties, haven't we? We said the first one was log base A of 1 equals 0, right? We said log base A of A equals 1. We said log base A of A to the x was equal to x, right? Those are the 3 that we already established. Yeah? Now, next to these, I want to write something down. I want you to tell me what it is. What's log 1? 0, right? Because isn't log base 10? And this property says log base anything, right? So this should also hold for log base 10. In fact, I could also have said what? Natural log of 1? What's natural log of 1? 0. Anytime you try and plug 1 into any log, doesn't matter which one it is, you always get 0. And you always get, yes, 0. So this is the general formula for any log. This is it. This is that property and how it works with the log, and this is that property on the natural log. This one, what would this one, to use this property, what would this have to say? Log base 10 of 10, right, would be 1. Y'all see that? How about with the natural log? Natural log of what? E must be 1. The log base 10 of 10 equals 1 seems to make sense because you can see it, right? There's your A and your A. The tricky part here is that what does ln really mean? Log base E, right? So do you see EE? Okay. What about this one? How would that work? It would be log base 10 of 10 to the x would be x, right? How would I say it for this one? Natural log of e to the x would be x. All I'm doing here is showing you these three properties on the two special logs and what they look like. Because it turns out that later on, if you were to do more math, which a lot of you won't, these three pop up all the time. I'll have students in my pre-cal classes and I'll be, okay, and natural log of e is 1, and they'll be like, why? And they just don't remember that property. So that's why I'm showing this. If you have your calculator, I'd like for you to try natural log of 1 on your calculator. See if you get 0. You get 0?
Yeah.
Try log 1.
Also says
0, right? Okay. This is going to be a tricky one. Try natural log of e. That's hard to type in depending on your calculator. Did you get 1? Okay. If you're working with your calculator, try and get natural log of e to be 1. If you can't, let me know. I'll come by and I'll show you how to do it on your calculator. Yours. Did you get the first one? Natural log 1 was 0? Okay. So I have to mess with the first. Natural log, and then yours. It's right there. Yeah, so you hit the, because it's yellow, you hit this first, then you hit that. The problem is it's saying e to what power? You just want e by itself, right? So just put 1. Doesn't either one do e? Okay, that's a tricky part of this. That's right. If you just do natural log and then e and hit enter, it's going to be error. I just get even. Understand? Okay.
So it's just natural log E1, if you have exponent video, equal 1.
That's right. Yes. So what you have?
I got that, but I was wondering the log is not natural log.
Yeah, I know, right? You feel like this is like the best calculator in the market for this log, right? I'll explain why you don't need it in a second. But it is in there. You have to, if you want to know where it is in here. You have to go to your catalog. Then if you hit alpha L to like scroll all the way down to the L, right there. Usually you have to hit it twice. I don't know why. Now you're in the L's, and just scroll down till you get to log. There it is. Yeah. Okay, anyone else need help on that? All right, try this then. What's natural log of e to the pi? See if you can do that on your calculator. The answer you should get should be pi or something about 3.14. 3.14. Yeah. This should either come out to be pi or 3.14. Let me know if you need help with that one. This requires you know where your natural log key is, where your e key is, and where your pi key is. You ready to move on? We have another property that's not up here, so I'm going to write our fourth property. Our fourth property is this. A raised to the log base A of x equals something. Guys, I know this is fun, but contain yourself over there. Any guesses here? Let me give you a slight hint. Do you remember the whole idea of a car wash in the inverse in functions? I talked about you take, let's say you take a car, we call it X. You go through a car wash, it comes out clean X, right? clean x. And then you put it through the inverse, and what does it come out as? The dirty car again, the x. So goes in as x, comes out something, goes through the inverse, comes back out x, doesn't it? Yes? Okay, right here, I want you to focus your attention. Does everyone agree that what I circled there is an exponential function? It's the exponential function a to the x, right? Yes? What am I plugging that exponential function into? The log base a, right? So this is your car wash. You take x, it goes into the car wash, it cleans the car, right? Then you take that and plug it into its inverse, and it comes out as what? The dirty car. Understand? Look at this property here. Where does x go first? Into the log, right? But that log is sitting inside of what? A to the something, which is the exponential function, isn't it? It's inverse. So what should it spit out? So car goes into log function, something happens to it, and then it goes back through its inverse. It should come out as exactly what it went in as, right? Yes? And it went in as x, didn't it? So it's going to come out as x. See, x goes into the exponential, something happens, log undoes it, it spits it right back out as whatever it was in when it went in. Same thing here. It's just the other direction, right? It's like we took the clean car wash, dirty car wash, right? That was the first example. This one was dirty car wash, then clean car wash. It's just backwards with the inverses. But in any event, they will work out to give you x. Okay. Let's see that property right there extended to the two special logs we have. This would be 10 to the log x, right? Why did I write it that way? 10 is a, right? Log base 10, I wouldn't write log base 10, I would write what? Log and then x. And then that should be what? X, right? 10 raised to the log x is going to be x. Now let's do it with the other one. E was the special base, right? E to the, how do I say log base e? Natural log x. This should spit out what? X. So that's our fourth property, the general property. Here it is applied to the two special functions. All right, now we get to go do some real work with this, all right? Do they do the change of base formula yet? No, I think I'm going to give you one more property. I'm going to jump. The book waits till later. I'm ready to give this to you now. I'm going to call this property 5. And this is a huge, huge property. It's called the change of base formula. Okay, like was suggested to me, why don't you have a log key, right? You only have the natural log key. Most basic calculators, scientific calculators have both, right? Yours is a pretty advanced calculator. So what it assumes is that the user is familiar with this formula. Now here's the formula. It says it's a way that we can change bases, all right? If I have a certain log and it's in a certain base and I don't want it in that base, I can change it to a different base. And here's the way it works. If I have log base A of x, does not matter what the base is, I can always change that by making it natural log x divided by natural log A. That's the Big Daddy formula right there. So let's look at how this works. Let's say I want to know what log base 2 of 8 is. Can anyone tell me what that is without doing anything on a calculator, just looking? 3, right? 2 to what power is 8? 3. Now, let's act like we didn't know that, and let's actually use this. According to this formula, I should just be able to go on my calculator and type in what? Natural log of, the x is the 8, divide that by natural log of 2. On your calculator, please do natural log of 8 divided by natural log of 2 and tell me what you get. You should get 3. If you don't get 3, let me know. You might have to do it as 2 separate computations. It depends on your calculator. Yes? You got 3? Anyone not get it? Yay or nay? Yeah? Okay. Very nice formula. Very nice formula. In fact, now I'm going to address, yours still doesn't have, yours has natural log 2, right? Yeah. Okay, never mind, I already addressed it. I won't get into it, okay? I won't get into it. This is the formula I want you to remember, but it turns out that you could have also done log x over log a, and it would have still given you the same answer. You have a log key, right? You could have done on here log 8 over log 2, and it still should have spit out 3. Very nice formula. But don't worry about the blue part. Just remember that part that's in the box.
I didn't get quite 3, I got 2
Okay, so did you type it all in at one time, or did you do it separately?
all together.
Let me see it then. It might be your use of parentheses. Let me see it. Okay, right after the 8, you have to close that parenthesis off. So do natural log 8, close parenthesis, then divided by natural log 2, close parenthesis. Got it now?
Yes.
All right. We're just going to keep grinding away, okay? So we'll go a little early today. Like I said, I'm going to stop class because I'll talk about grades. But y'all can hang, right?
Sure.
No, or do you want to stop? We can stop. What do you want? My battery's on its. Okay, we keep going. All right. So now this is the main idea of why we've been looking at logs. Not to graph them. It's to do this. Solving exponential and log equations. Now, what I want to do is try and give you an appreciation of what it is what we're about to undertake. So I'm going to put here recall. As a math student right now, as a math student, could you solve this equation? Could you solve that? How would you do it? Add 1 to both sides, divide both sides by 3, right? That's a linear equation. Every student here should be able to do that. Okay? How about if I asked you to solve this? How would you solve that? Try and factor it, right? Set each of the factors equal to 0. Or if it didn't work, quadratic formula, synthetic division, right? What if I gave you how would you solve that? Try grouping or factor by synthetic division, something like that. In fact, for any power, right, any polynomial, we would use like synthetic division or something. We have a way of attacking problems like that, right? For all those, we have a way of attacking and getting solutions. How about something like this? Square root of x minus 1 equals 0. Could I move the 1 to the other side? Square both sides? Yes? How about if I had something like x over x plus 1 equals 4? Could I solve that? Multiply both sides by x plus 1, right? Try and get x by itself. All of these equations are different, right? Linear equation, quadratic, cubic. We could do 5th degree, 4th degree, 10th degree. Square root equations, rational equations. All of these, we have these algebraic ways of attacking them, right? Yes? Well, how about this? Can you solve this? Up to this point in your life, What's the big difference now? What's the big difference between this and everything that I just put up on the board? Where does your x live? It lives in the exponent, right? All the other problems, the x was down on the ground, wasn't it? Now you have an x up here. So I'm trying to figure out what number do I plug in here. So I multiply it by 2, subtract 1, raise 5 to that power, subtract 4, I get 10. I mean, you're just never going to do that in your head, right? We do not come in here and try and factor. We do not come in here and try synthetic division. We don't do squaring on both sides. The only way to attack this is to use properties of exponents and logs. That's the only way to do it. So watch what I'm about to do. Since I'm trying to solve for x, I'm going to try and isolate that term. So right now, this is going to be pretty similar to what we've done before. I should probably get that -4 out of there, right? Add 4 to both sides. I get 5 to the 2x minus 1 equals 14. Okay. Now we're stuck. Right? So go back and think about converting from exponential to log form. From exponential to log. How do we convert from exponential to log? This is the first thing I talked about today. If I were to rewrite this in log form, it would be log, what would be my base? 5, right? It's always that number that the exponent's on? 5. And then what would go here and what would go on the other side of the equal? 14 goes here? And then what goes over here? 2x minus 1. Now how can I check to see if I wrote that correctly? Do the loop real quick. Is that loop going to give you back this? Is 5 raised to that equal to 14? Is that what I had over here? Yes? So I have written that down correctly. Yeah?
Yeah.
What have I done, ladies and gentlemen? What have I done? Look at your x. I've basically taken it out of the exponent, haven't I?
Yes.
By using the property of logs and how I can rewrite things in logs. I've introduced the log. That's the downside. To get x out of the exponent, I had to bring a log into play. But I've actually pulled the x off the exponent. You see that? So I can get x by itself here by what? Adding 1 and dividing by 2, can't I? Now the left side, can you do anything with that? Who's going to give me the, who's going to have the Eureka, is that what it is? Like when you have that light go off, what's that called? Eureka, right? Y'all heard that before?
Yeah.
Who's going to have that Eureka moment and tell me what to do with the left side? For extra credit. So if I say extra credit, you'll think about it more? That's change of base formula. That's a formula I just gave you, isn't it? Isn't that something you can compute on your calculator now? Isn't it? So I'm going to rewrite this. The left side should be natural log 14 over natural log 5 equals 2x minus 1. Everyone agree with that? Change of base formula on that right there. Okay. So get on your calculator and do natural log of 14 divided by natural log of 5. What is it? It's going to be a decimal. It's going to be ugly, so let's just round. 2.16? Sounds good to me. Anyone else get that?
I got 1.6.
Uh-oh. 1.6? Uh-oh. 1.6? You're being outvoted here.
That's my fault.
Okay, 1.64? Is that all right now? 1.64? Now, what type of equation is that? Linear, right? Now we're back to a linear equation. So add 1 to both sides. If you add 1, you get 2.64 equals 2x. And now just divide both sides by 2.
1.32.
1.32. Now, we did round a little bit, okay, didn't we?
Yeah.
We rounded when we got this off our calculator. That's okay. That's close enough. So let's see here, and we have solved this equation. The original equation was 5 to the 2x minus 1 minus 4 equals 10, wasn't it? Will someone please take on their calculator, I want you to do 1.32 times 2. Subtract 1, and what do you get?
1.64.
1.64? Okay, someone on their calculator do 5 raised to the 1.64 and tell me what they get. 5 raised to the 1.64. 14.00, and then subtract 4 from that, what would you get? 10. We solved the equation. We're off a little because we rounded, but that's okay. We want to be more precise, we just get more decimals. Do you see how we solved this now? I mean, instead of going, well, let me just try some numbers and see if they work, we actually had a process to do it. That's pretty nice, right? Maybe I get more excited about that than you do. As it should be. Try something a little more elaborate. How about solve this equation? E to the negative 2x, and let's put a 3 in front of that, the whole thing, plus 4 equals 5. So you're asked to solve this. What type of equation is this called? We will call these things exponential equations. Why do you think we call it exponential equation? Because the x is an exponent, right? So it's an exponential equation. So it's not a linear equation, not a quadratic, not a polynomial equation, it's not a rational equation, not a radical equation, it's an exponential equation. And so what is the attack that we're going to have here? Subtract 4 first. So we're going to try and isolate, careful here, we are going to try and isolate the exponent. That means at 3, we don't even want that 3 there, which we'll divide. But so subtract 4 on both sides first, we get 3 e to the negative 2x equals 1. And now to get rid of the 3, divide by 3, don't subtract. So you have e to the negative 2x equals 1/3. And then now at this point, what did we do? Changed it to log form, right?
Yeah.
To log form. When I go to log form, it's going to be log base what? E. So I'm already thinking that's actually going to be a what? A natural log, right? Log base E. But let me finish it off. What goes in here? What goes? I have the equal here. What goes here? 1/3. And then what goes out here? Negative 2x. Okay? Now on the left side, it's going to be a little different than last time. Because last time, didn't we take the left side and do change of base formula?
Yes.
You don't have to here. Why? Because it's log base E is what? Natural log.
Yeah.
So this is actually just natural log of 1/3 equals negative 2x. Isn't it? And now you can go straight to your calculator, do natural log of 1/3. I wonder if anyone's going to type in natural log of 1/3 and get 0. Anybody get 0? It's wrong if you get 0. You get a negative number? Okay, that's good. I just want to make sure no one gets 0 when they do natural log of 1/3.
I got error.
You got error? Is it on your phone? You have to actually do the number first, then take the natural log.
I have the LN button.
Okay, so just do me a favor. Just clear everything out and type 1. and then hit the natural log button, what happens? You get 0? Error. What kind of phone is that? Android? No? Android or something? I don't know. I have to, but the thing is, I don't want to help you on the phone because you can't use it on test. So, all right. So what did you get on the left? Negative what? Negative 0.1.
Negative 1.09.
Negative 1.09. How many got something like that? Yes. Okay. And then the other side of the equation is just negative 2x. So now just divide both sides by negative 2 and you're done. What you got? 155 positive, right? Approximately. This is you don't have to, you can put equals, I won't take off, but I mean we are actually squiggly equal because it is an approximation, but close enough. All right? What do you think about that? Fun? All right, so those were exponential equations. Now, let's try something else. Let's try a log equation. This is called the log equation. So, for a log equation, what do you think you're going to see in the equation? A log, all right? So check this out. If I have log base 7 of x plus 2 minus 4 equals negative 2. Let's try that. So with the exponential equation, the x we were solving for was where? In the exponent, right? Up in the top. With the log equation, where's the x? Inside the log, right? Inside the log. This is our base, right? This is the thing that's inside the log. This is what we call the argument of the function. It's a thing that's inside of it. So my x is trapped in there, isn't it? Okay, I'm going to untrap it. But the way to untrap it is I first have to isolate the log term. So I still need to get rid of that negative 4 by adding 4 to both sides?
Yes.
Okay, so I get log base 7, x plus 2 equals 2, right? Anybody have any idea how I can get that x out of that log?
Exponent form.
Go to exponent form this time, right? With exponential equation, we wrote it down, we isolated it, then we went to log form. Here, we're in log. The x is in the log. We need to get it out of there, so we're going to go to exponent form. To go to exponent form from here, you can just use the loop, just straight away. This raised to that must equal this, right? That's what that means? So write that down on the next line. What would our next line be? 7 squared. So 7 squared equals what? X plus 2, everything that's in there. Now, mistakes I see, students will do this, and they'll write 7 times 2, right? And they'll put 14 here. It's not 7 times 2, it's 7 squared. 7 squared is 49. Last step,
Minus 2.
minus 2. Your answer is 47. Okay? Like this one. Negative 10 natural log 3 minus 2x plus 14 equals 5. Okay, so we have a log equation. The x is trapped inside the log. I'm going to have to get it out of there. In order to do that, at some point I'm going to have to do that loop, right? Possibly. But before I can do that, I have to isolate the log. That means I have to isolate this part. I will not want that negative 10 over there. So let me go ahead and subtract 14. When I subtract 14, I get negative 9. Now divide both sides by 10, negative 10, right? Divide by negative 10, and you get negative 9, or sorry, you get 9 over 10. What's 9 over 10? 0.9? 0.9. Do we have the log isolated? Yes. So now the loop. What's the tricky part of the loop here? The loop? That's right. Look, I'm supposed to do the loop, but where the hell's the base? What is the base? E, because it's natural log, right? So you just need to remember that this really means log base E, right? Which means it's going to be this, right? Which for us we could write E to the 0.9 must be equal to 3 minus 2x. Do you see what I was saying earlier? That the thing I think confuses most students is that, like, if we just would have left it as log base E and just wrote it that, or log base 10, you would never have to remember, oh yeah, that base is there, and then do the loop. Like, it would always just be there right staring at you. But here we have to remember that it's base E. And now on your calculator, e to the 0.9, 2.46. And now this is all just linear, right? What would I do? Subtract 3. If you subtract 3, you get negative 0.54. And then equals negative 2x. Divide both sides by negative 2. 0.27, positive, right? While I'm thinking about this, I'll give you a little mental break from this for a second. If you were to look at the number line, here's a number 1, right? Does anybody know what the number right next to 1 is? The closest number to 1. The one right next to it. Or is there one? Is there a number right next to 1? 0.9 repeating? What do you think about that? Is 0.9 close to 1? 0.9 is here, right?
Yeah.
Is 0.99 closer? Oh, I'm sorry. I apologize. I forgot to turn this off. .99 is closer? 0.999 is closer? 0.999 is even closer? So how about just 0.999 forever? Would that be the closest number? Understand? Maybe, maybe not. So, see if I can get you to believe this or not. Just a quick exercise. If I say x is equal to 2.4, what's 10 times x? 24. So if I take a number and I multiply it by 10, what do you do? Move just 0.1 over to the right, correct? Okay. So let's see if I can discuss this whole 0.999 forever thing. I'm going to call right now x, I'm going to say x is 0.9999 forever, right? Like that. Now, what is 10x? So if I multiply both sides by 10, what should I get? 9.999 repeating, right? Yes? Now, over here, erase, in your mind, forget the 0.99. Let me just talk about 10x and x. If I say 10x and I subtract x, how many x's is that? 9 x's? Okay, now, what was 10x? Over here? 9.999 repeating. If I subtract from that x, which was what? 0.999 repeating, then what would you get? You would get 9, right? These would cancel out, and you get 9. So 10x minus x is 9x, right? But that means that 9x would have to be equal to this, which means x is what? 1. What I'm trying to do with this is start off by saying x is this, right? And then just do some simple calculations to show you that if x is that, x is actually this. So 0.999 forever repeating is actually 1. It's not the number closest to 1, it is 1. This is a weird thing. But so, and mathematicians will argue this. We'll argue with each other about this too. But if you're ever like on some like trivia show and it's like the $1 million question, you win it, then we'll talk about how much you owe me. No, it's just to get you to stop thinking about logs for a second.
Okay.
There is no number closest to 1, though. There is no closest, because if you have the number 1, right, and let's say you find a number right here, and you call it n, okay? And you say that's the closest number to n, or to 1. I can always find a number in between by taking the average of your number and this number. So adding these two together and dividing by 2 will always be a number in between them. And I can do that for any number you ever get.
Isn't
Yes?
that kind of like the thing where if you travel halfway to the door each time, you'll never reach the door?
It's kind of like that, yes. I mean, in the sense that there's an infinite number of numbers in the number line.
Yeah. It's like if you travel, if someone tells you travel halfway to the door each time, so you travel halfway, you'll never actually reach the door.
Yeah, if you walk
It's
halfway
not
across the room, right, walk halfway, and then walk halfway again, then walk halfway again, then walk, will you ever reach the other side? It's the same thing when I tore that piece of paper and I was saying half of it, right, radioactive decay, half, and then half, and then half, and then half, and then half. Keep doing that forever, it starts going to nothing, but you never actually get there. Okay, back to logs, sorry. How about this equation? 4 log 4x minus 3 minus 8 equals 0. You want to try that one on your own? See if you can get it? I'll give you a second. I'll give you a minute. Do we have a solution?
Is it 25?
What'd you get?
One. I'm not sure.
1?
Yeah.
I got 25.75.
25.75?
That's what I get.
Okay, let's see. What was the first thing you would do here? Or add, right? Add 8? Right, okay. Add 8 to both sides. Then divide both sides by 4. Which is 2. And then put it into exponential form. So you have to do the base like this loop thing. But what's the base? 10. 10. So since that's base 10, it's 10 squared, right? Not 10 times 2. And then that's, what, 100 equals 4x minus 3. And then you just add 3, 103, divide by 4, 45.77. Okay? Does that seem okay? All right. Now, I'm kind of back and forth here because there's a lot of information still to talk about. Why don't I give you a couple more of the properties? We'll talk about them briefly. And that way when we come back next week, it won't be like brand new material that I'm giving you. It'll be something that we've been exposed to. But the remaining properties will really allow us to solve some pretty complicated problems. These are what we call basic exponential and log equations. They're basic in the sense that we just isolated, then we converted form, and then we just did it. The ones we're going to do later are going to be much more challenging, all right? But to do them, we have to have these properties. So we had stopped on property 4, right? 5 was change of base? Okay, so we're going to go property 6. More properties. 6. Let's say you have a log, let's say you have a base, and inside of it, which we call the argument, you have 2 things in there that are being multiplied. Multiplication inside of a log. This property says that what you can do is you can take that log and you can split it up into 2 logs with addition between the 2 logs. So single log multiplied inside becomes 2 logs addition. Then the x goes on one and the y goes on the other. Got it?
Yeah.
Okay, if you are taking this property can work both ways. If you have 2 logs that have the same base and there's addition, we can put them together into a single log over here like this. So if we are using this property moving from left to right, we call it expanding a log. If we use this property moving from right to left, we call it condensing. Does it make sense that that would be like that? Expanding because you started with one log and expands out to two. Condensing because you start with two and you condense it down to one. Yes? All right, now that's your sixth property. Let's look at the seventh property. The seventh property is what happens if you have division inside. Well, what does your instinct tell you? It's going to be subtraction. And that's exactly what it is. So if inside of a single log you have division, this will become subtraction. Now what's very important with this property is that this order over here matters. Okay, so the x was on top, right? The x goes first. The y was on the bottom, the y comes next. With the multiplication, it doesn't matter because it's addition between them. With subtraction, the order matters. Again, expanding would be going from left to right. Condensing would be going from right to left. Questions? Eighth property. I believe this is the last one. If you have log base A of x to the n, what's that going to be? Well, let me show you down here where we're going to have an answer here, what this is. Let me show you down here where it comes from. What does x to the n mean? What does x to the n mean? X times x times x. How many of them? N of them, right? Isn't that what that means? And so every time we have a multiplication, that sixth property said we could do what? If we have multiplication, we can do split and becomes addition, right? So for every multiplication, shouldn't I be able to create its own log for each one? So I should be able to say log base ax plus, and then another one log base ax, and then plus another one log base ax. And how many of these log base ax's will I have? N of them, right? So does it make sense then that this property says that this becomes n of the log base ax's? N of them. N of those things. Is that a question?
I missed number 7. The 7.
With 7 division? Yes? Oh, you want the formula? Log base A x over y equals log base A x minus log base A y. Can you read that okay? All right, you see how this works? The way I want you to think about it, though, forget all that crap right here. That was just to prove to you, I guess, that it is this way. The way that most people remember this is that what happens with this property is that you see that power there? Where does it go? Here, in the front. In other words, you can take that power and you can drop it down in front. Yes? The power drops down. Or if you have something in front of a log, you can go the other direction and do what with that number in front? Push it up to this x. Either direction.
You can like figure out log and just multiply by n.
That's right. All right. Oh wait, not base 5, sorry. Log 5 plus log x minus 9 equals 1. What are we looking at here? What is this? What is this? It's an equation, right? Has logs in it. The x is trapped in the log, so this is a log equation. What's the difference between this and what we did just before this? There's two logs. But we're not afraid of two logs now because we have these formulas, right? Formula 6 says if we have two logs and there's addition between them, we can condense them down to a single log. Now I have to do that because right now you cannot do the loop. The reason you can't do the loop is because you have two logs. You can't do two loops. I never said you could do two loops. So we have to just do one. So condensing. What will these two together become using property 6? Log, and then inside this times this, right? Multiplied, you would distribute. So 5x minus 45. And then what's still on the right side? 1. Questions? Now you can do the loop. That's right. And because there's no base, it's a 10, because it's log. So this should become 10 to the 1 equals 5x minus 45. Ten to the 1. Okay, add 45 to both sides. Divide by 5. Right? It's 11. Add 45 to both sides, you get 55 equals 5x. Divide both sides by 5, you get 11. If you're not having fun yet, you're never going to be able to have fun. Okay? Goodness. Okay, let's do one more, okay? We'll do one more, we'll call it a day. Well, let's see, it's 5 after. It might be a little early. I know you want to stay and keep doing this, so. How about log x minus 7 equals 2 minus log 3. Can't think anymore? Okay, division because you see subtraction. Hold on, they're not on the same side of the equation yet. Yeah, the problem right now is we have logs on both sides of the equation, so we need to get them together on one side and then use our property. So we'll have to add log 3 to both sides. Add log 3 here. So we get log x minus 7 plus log 3 equals what was still on the right side? 2. Now you can put them together. And what would those become due to property
Log 3x.
log 3x minus 21 equals 2. So now you do your loop. 10 to the 2 is 3x minus 21. Y'all following? 10 to the 2. What is 10 to the 2? 100 is 3x minus 21. Add 21 to both sides,
121 divided by
divide by 3. What is that, like 40? Or is it 40.333 or something? So this is about 40.333 forever. Make sense? Yeah? We'll just do 7 more. I haven't given you one with division yet, and I think it's worth you seeing one with division. Right? I'm trying to keep all the problems I'm doing today at a certain level. That way when we come in on Tuesday, we can blow the doors off. All right? We'll see how nasty these things can get. They're really not that bad. I mean, I don't want to scare you away. Natural log x minus natural log x minus 1 equals, oh, you know what? Make this inside here 2x minus 1. Equals 1. This is going to be pretty bad. Do you see your x is trapped actually in both the logs, right? It's in both of them. What's the operation between the two logs?
subtraction.
Subtraction. We can take two logs with subtraction between them and make it a single log. But we have to convert the subtraction to a division, right? So we have a single log here. Division inside. What goes in the top?
The x.
The x, this one. And then the bottom?
2x
2x minus 1. That must equal 1. Right? Now what?
Yeah.
Do what? Exponent. Oh, exponential form. So I do my loop. What do I use for my loop? E, right? E, because it's natural log, e to the 1 is equal to that stuff inside. Yeah. E to the 1 is equal to x over 2x minus 1. Oh man, that is a rational equation in x, right? X is on top and bottom.
Yes.
So we have to multiply both sides of that equation by what?
2x.
2x minus 1. So if I multiply this by 2x minus 1, I get something. If I multiply this by 2x minus 1, it cancels. The left side is 2x minus 1 in parentheses times e. And then the right side's just x, right? Have I solved for x there? Remember, we got x here and over here, so we haven't solved for it completely. So isn't e just a number? E's like what? 2.718. Let's go ahead and just put 2.718 there instead. Times 2.718. Then that equals x. Now what can I do on the left side? Distribute this 2.718 through. What's 2.718 times 2? 5.43, and that'll be x. Okay, I'm rounding a little bit, times x, and then times -1 gives you negative 2.718. That equals what?
X.
X. I'm off my screen. And then I can get this piece to the right. I can subtract x on both sides, right? This is like a 1x. So subtract 1x, I get 4.43x equals 2.718. And now divide both sides by 4.43 and we're there. What do you get? What is it? Point. What is it? 0.614? Anyone else get that? Yeah? Okay. All right, let me give you your homework assignment for tonight, or for the weekend. Okay, on page 445, you should take a look at (11) through 19, odd, 23 through 33, odd. Now, all those problems are asking for is for you to convert from one form to the other. That's it. It's just like, here's exponential form, write it in log form. Don't do anything else. So that those will go pretty quick. All right. Then (55) through 61, odd. Two of those problems are just use your calculator to find like natural log of 225. That's just making sure you know how to use the key. Then the other ones find log of square root of 37. So make sure you know how to use the key. Numbers 59 and 61 are graphing logs. That's where you have to, come up with your inverse, make a t-table, switch the points. Okay, so two of those problems are pretty in-depth. And that's it from that section. And then from 4.4, I don't have the entire homework for you for this section. You'll get more later from this section, but for now, you can take a look at 462. (9) through 19, odd. All of those, that's a mixture of exponential and log equations. Why don't you try 21, 23, (87), 89, 91, and 95. All right, my battery's giving me a warning that it's about to die, but this worked out perfect. So what I'm going to do is I'm going to pack up all my stuff and go down to my office. If anyone wants to go talk grades, we can go talk grades there because that's where I have most of the information that I would need to talk to you about. So, any questions? Yeah, everyone have a good weekend.
Sure, I'll bring the note on Tuesday.
Okay.
Actually, I have the note